Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 105 in our incredible new tutorial series where you are unleashing the power of your Raspberry Pi Pico W. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice. No sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at SunFounder. SunFounder is actually sponsoring this most excellent series of video lessons. And in this class, we will be using the Kepler kit for Raspberry Pi Pico W. Now, hopefully most of you guys already have your gear, but if you don't, take a look down in the description. There is a link over to Amazon, and you can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot easier if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. And what today's lesson is about is how to control the NeoPixel arrays using the Raspberry Pi Pico state machine. Now, we've spent probably a dozen or more lessons already learning the Raspberry Pi Pico PIO state machines and how to program them, but we've been doing little things to just learn the commands and make it do simple things. But what we're going to do today is we're going to have a project that you really would have to use the state machines. You could not control the NeoPixel arrays without being able to program the state machines, because the NeoPixel arrays require very precise timing. Now, this is going to be a little bit of a long lesson and a little bit of a tedious lesson. And probably what I'm going to do is I'm going to explain to you how the NeoPixels work. And then somewhere in the middle of the video, you can pause and try to do the homework. But then in the balance of the lesson, I'll show you my solution. Because this is tedious, but I want to teach it to you. But I don't want to frustrate you guys that are maybe not state machine experts yet. But you guys that are out there, and I think you know who you are, you can pause the video and then see if you can do it on your own without looking at my solution. But in order to do that, we're going to need to start by understanding how the NeoPixels work. So the first thing I should do is the very most simplest part of the whole day, and that is, we got a boater out there. It's a little bit cloudy out there today, but we'll hope him luck in his fishing endeavors. But this is our Raspberry Pi Pico W. You can see that the NeoPixel array, we can power 8 pixels from the Raspberry Pi Pico W. So I have that cooked to the 5 volt, and then I have the black wire connected to the ground, and then I've got the control wire, the yellow wire, connected to GPIO pin 0. So that setup is pretty easy. But now, how do these marvelous, amazing NeoPixel arrays work? Well, let's jump over here, and what we're going to do is we're going to start, just to make it sophisticated enough for you to really learn this. And I guess I better, that's going to work, I think. Sophisticated enough that you can understand it, but not so complicated that it's like you don't understand it. So if I did 1 pixel, you wouldn't really understand how the data is passed. And if I did all 8, it would get tedious. So we're going to consider a NeoPixel array of 3 pixels, even though we have we have 8 pixels, but I think by extension, you would be able to learn this. All right. Now, what it is that you have to create a data array that includes little chunks of what color you want each pixel. And so let's just do a very simple case. And so what I'm going to do is I'm going to come in here, and I am going to, this is getting extremely annoying. Okay. Now I think this should work. Okay, so I'm going to create an array called my color. Okay, and now it is going to be equal to, and I have a bracket. Now, what color do I want the first pixel? I want it red. So what would that be? 255, which is an 8-bit number. That's important. And then 0, which is also going to be an 8-bit number, and then 0. So that would be red. And then the next pixel, I want to be green, and so that would be 0, 255, and 0. And then the last pixel, I want to be blue, which would be 0, 0, 255. Okay, now, how does the NeoPixel work? Well, the first thing you see that you have one pin of the N pixel hooked to 5 volts. You have another pin of that same, N pixel hooked to ground. But then where does the magic happen? The magic happens on the DIN pin, the data in pin. And we're going to connect that to pin 0 on our GPIO pin 0 on our Raspberry Pi Pico. Now, what do? You take this whole array of data, and we've got to start thinking in terms of bits. This is 8 bits, 8 bits, 8 bits. So each pixel is going to get what? 24 bits. And then this one's going to get 24 bits. And then this one is going to get 24 bits. So you pass this whole, you shift it in 1 bit at a time from pin 0 to DN. Okay, now what does DN do? DN takes the first data point, the first little packet of color, this one, and what does it do? It keeps it and then takes it off the array, and then it passes the balance down to the next pixel. Well, what does the next pixel do? The next pixel keeps the 0, 255, 0. Okay, it keeps that and it marks it off the list. And then what does it do with the last one? The last one, then it passes down here. Okay, so what does that mean? That means that the first pixel has now 255, 0, 0. And what is that? That's red. And then the next pixel has what? It has 0, 255, and 0, green. And then the last pixel got what? 0, 0, 0, and 255, like that. So now each pixel has its own little packet of data telling it what its color is. And if there was 100, then this array would have 100 colors in it. And then the first pixel steals 1, the next pixel steals 1, and then it goes all the way down. Now, the thing to notice is this first data point goes to the first pixel, which is the one that is closest to the wires, the one that is closest to the wires coming out. Okay, I hope that makes sense. And now what I want to do is I think we got to talk about this a little bit more. So I'm going to see if I can come up to a clean version. And now what we're going to do is we're going to write that color down again, because now remember we've got a nice Python-like friendly array, but we've got to turn that into a bit train, because the NeoPixel understands what? It understands zeros and ones. And so let's come back to my color and we'll write it down again. And what did we say? The first was going to be red, 255, 0, 0. And then it's going to be green, which is 0, 255, 0. And then the third one, pixel, is going to be 0, 0, 255, like that. Okay. Now, what we said is that this is 8, 8, 8, that is 24 bits. Now, why do you say 0 is 8 bits? Because everything's going to be 8 bits. Now, the biggest number I can have in 8 bits is 255, and the smallest number I can have in 8 bits is 0. And so we just have to understand that. Then this is 888 for 24 bits. And then what is this? This is 8888 for 24 bits. Okay, so what you see is each pixel needs to receive 24 bits. So what does that first pixel need to receive? And in other words, exactly like all we can push down this data line, is zeros and ones. And so what would this first data point be? It would be, we could say 0b, saying that this are bits, right? 0b says it's going to be bits, and we could pass it 1, 1, 1, 1, and then 1, 1, 1, 1, 0, 0, 0, 0, and I'm going to wrap around 0, 0, 0, 0. So this is the 256. This is the first 0, and then the second 0 would be 0, 0, 0, 0, 0, and then 0, 0, 0, 0. So this would be 1, 2, 3, 4, 5, and then I would need 1, 2, 3, 4, 5, 6. So that is going to be right. So this is I'm just trying to make sure. 6 times 4 is 24. 1, 2, 3, 4, 5, 6. Yeah, that's right. So this checks out. Okay, now what is my next one going to be? That's green, so I'll go ahead and make it in green. That's going to be 0, 0, 0, 0, and then 0, 0, 0, 0. That's the first number. Then we're going to have 1, 1, 1, 1, 1, 1, 1, 1. So that's going to be the 255, and then the 0, 0, 0, 0, 0, 0, 0, 0, 0. Very good. Now the last one's going to be blue, okay? And so that's going to be, again, 0, 0, 0, 0, 0, 0, 0, 0, and then it's going to be 1, 1, 1, 1, 1, 1, 1, rookie mistake, and then 0, 0, 0, 0, 0, 0, 0, 0, and then 1, 1, 1, 1, 1, 1, 1, 1. Okay, so we've got something like exactly 24 times 3 would be 1272 bits that we're going to pass all together, but it is 24 bits per pixel. Okay, does that make sense? Okay, so I better get out of your way before I start covering up the work. And I'm going to go ahead and get another sip of coffee. Now, it's hard to keep track of all these zeros and ones. And so really it's completely equivalent to use hexadecimal as opposed to binary. And it's just easier to keep track of hexadecimal. But hexadecimal is a 0. A hexadecimal is a 0x instead of a b, and hexadecimal bunches 4 bits together into one number. Okay, so how do you count in hexadecimal? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9, because I started with 0, I've got 10 fingers up. Now you might say 10. No, A, B, C, D, E, F. Okay, so what is the largest number that we can have? The 1, 1, 1, 1, right, which is the 1, 1, 1, 1. That would be what? That would be 15, and that would be the F. Okay, so this becomes F. And then what does this become? This becomes F. So I have an FF, which is the FF. If you went 1, 1, 1, 1, 1, 1, 1, 1, and you found the binary equivalent of that, that would be 255. And then that in hexadecimal is FF. And you can work it out if you don't believe me. But then what is the next number? The next is the hex 0. Okay, this becomes the hex 0. And then this becomes the hex 0. I'm sorry, this is the hex 0. This is the hex 0. Let me erase that. I'm still on this first bit. So I've got FF. Now, this becomes this 0. This then becomes a 0. And then this becomes a 0. And this becomes a 0. So, right, what do we have? We have 6 hex characters because each hex character represents 4 bits. So 6 hex characters represents 24 bits. But do you see how much easier it is to write this than it is to write 111111000, it's just this is easier. So someone now tell me what this color would be. This color would be 0x, and then I've got 00 FF 00. And then what's this one? 00, and I should put the 0x. So I'll put the 0x, and this just tells your board, it tells your microcontroller that you're sending it a hex number. This would be 0000 FF. Okay, does that make sense? So what you have to see is this is the actual data packet that this ends up with. This, which represents green, is the data packet that this ends up with. And then this becomes the data packet that this ends up with. All right. Now, how do I get this number? Like, what do I have? I've got this. And how do I turn that into, I've got 3 integers. How do I turn that into one hexadecimal number? Well, now really, to the microcontroller, 255, the integer, it's interpreted as 1111 1111 0000 0000 0000. So to the microprocessor, these two numbers are exactly the same because the integer and the binary equivalent are just completely interchangeable. Okay, that is exactly the same as 0x FF 0000. Okay, so very good. 255 is the same as the binary, is the same as this. You don't have to do any fancy conversion. But now, what is the problem? I said that wrong. The 255 is just 1111, and it's 00FF. Okay, so 255, let me write this again to be really clear. Let me see if I can get rid of this. I don't have a good way to erase it, so I just got to back over it. Okay, so now what I will say is 255 is 0xFF, and 0 is 0xF, or 0x 00. And so those are the numbers. All right. Now in hexadecimal, to send this in hexadecimal is very easy. What would it be? 0x FF 0000. That'd be really easy, right? That would be really easy. But what is the problem? The problem is I don't have hexadecimal. I have 255. Now it knows that 255 is 0xFF, and 0 is 0x00, and 0 is 0x00. But how do I combine the 255, the 0, and the 0 to get this. Well, what we're going to have to do is we're going to have to do logical operators, okay? And so let's say that, let's think of these numbers up here. This is the R, this is the G. I'm going to write that again. That's getting too messy up there, okay? Okay. I've got 255, 0, 0. All right. This is the red, this is the green, and this is the blue. But I need to get those commas out, and I just need to make one big hexadecimal of 0xFF00. Well, how do I do that? Okay. Well, what I do is I take the red and I shift it left by 16 bits, right? So it's 8 bits, and I shift it left by 8, and I shift it left by 8. And then what do I have? I have out here to the left 255, or out here to the left, I have 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, okay, and then 0, 0, 0, 0, 0, 0, 0, 0, like that, okay. Now, what do I want to do with the next one? Okay, what do I want to do with the next one, which is the green? Okay, it is this one. What do I want to do with it? I want to shift it to the left by 8. And what do I want to do with this one? I just want to leave it. Okay, I just leave it. Right? Now, what I do is between these two, I don't add them, I OR them. Okay, so this one is going to be out to the left, and then it's going to have 16 zeros following it. And then those 16 zeros are going to be filled in with these bits, okay, these 8 bits. And did I say this right? The R is 255. I did not say that right. So let me try that again just to be clear, because I added too many things, right? I added too many things. And so let's try this again, because it's simpler than what I just said. I showed you the whole shifted number. Okay, so I'm going to, okay, what am I going to do? I'm going to shift the red. The red is what? The red is 1, 1, 1, 1, 1, 1, 1, 1. That's the red, 8 bits. I'm going to shift it to the left 16 bits. So then after the 1, 1, 1, 1, I've shifted it left by 16 bits. So I'm going to have 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to have 1, 2, 3, 4, 5, 6, 7, 8. I'm going to OR that with what? With green. And what is green? Green is 0, 0, 0, 0. And so I OR 0, 0, 0, 0. And remember, I shifted that to the left by 8. And then I've got blue that I don't do anything with. So if I shift green to the left by 8, it's going to go here, and blue just stays where it is. So by doing this, take red, shift it to the left, 16, take green, shift it to the left by 8, take blue, leave it where it is, and now what do I have? I have the 24 bits of ones and zeros that I can, I have the 24 bits of ones and zeros, which I can now pass in to DN. And so that is what we need to do. All right, now that is the data stream. So you can see I can create an array, right? I can create a color array. And then I have to replace something like 255, 0, 0. I have to put that in the array as 0, X, F, F 0, 0, 0, 0, like that. And then the next one would be 0x 0, 0, F F 0, 0. And then 0x 0, 0, 0, 0, F F. Okay. And I need to get even more tiny, don't I? Okay. So you see, I have to take these numbers and I have to change them into these numbers. And I showed you how to do it with this magic combination of shifting the 8 bits to the left, and then ORing all 3 of the numbers together, and then you will end up with exactly what you want. Okay, now there's one other thing that you're going to need to know, and so I need to go ahead and show you that, and that is now. So you see, what would I want to send this? I would want to send this for this number here. I would want to send it 1 1 1 1 1 1 1 1 0 0 0 0 0 0 0 1 1 1 1. I would want to send this bit train, but how do I send that bit train? I have to understand, how does the NeoPixel look for a 1, and how does the NeoPixel look for a 0? And that is according to this timing chart, okay? And so if we look at this timing chart, what we can see is that if I, okay, wow, that was crazy. Okay, I think this will work. So if I want a what? If I want a 0, I need to send it a high code, a high signal for 0.35 microseconds, a high code for 0.35 microseconds, and then a low code for 0.8 microseconds, right? Do you see these down here? Now, if I want to send it a 1, the high is going to be 0.7 microseconds, and the low is that's going to be T1 low is going to be, T1 high is 0.7 microseconds, and then T1 low is going to be 0.6 microseconds. Now, is that right? 0.8 and 0.35 are 0.125, and 0.7 plus 0.6 that's roughly 0.125. So it's just that rounded off a little bit. Okay, so this is what I'm going to have to do, so that what we did before, 1 1 1 1 0, I'm going to have to convert into this pulse train using the what? Using the state machine. So the first thing now we got to know about the NeoPixels, what we've got to know about the NeoPixels, they want this pulse train coming in at 800,000 hertz. Okay, and so what does that mean the period is? The period is equal to 1 over the frequency of 800,000. And if you put that into a good calculator, you will see the period is 1.25 microseconds. So what do I want this to be? I want this to be 1.25 microseconds, and I want this to be 1.25 microseconds. So that's the period, and then it's just going to depend on how long. It's going to depend on how long that up pulse is and how long the down pulse is, and that will determine whether you've got a 1 or a 0. Okay, now what do we have to decide about the state machine? To be able to create that pulse train, the first thing we're going to have to decide is what frequency do we want to run the state machine at? Well, if I ran it at 800,000 hertz, then each clock cycle would take the entire period. And by doing that, I couldn't generate that waveform within that. So I have to operate what? I have to operate faster. So what would be a good thing? Well, let's operate it 10 times faster, and that way we can break that period up into 10 time segments. So we are going to set the state machine at 8 million hertz. And then that would mean that each clock cycle is going to be 0.125 microseconds. Okay, 0.125 microseconds. And if I have 0.125 microseconds, then I am going to have 10 clock cycles in one period. All right, 10 clock cycles in one period. So then what would we want to do? We would want to think about this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? We would want to think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now let's think of a 1. Let's think of a logic 1. A logic 1, for the logic 1, you want it to be high for how long? 0.7 microseconds. Now, how many clock cycles would that be? Well, that would be 0.7 divided by 0.125, and then that's going to be equal to 5.6 clock cycles. So what are we going to do? We're just going to call that 6. So there's going to be 6 cycles that we want the clock, that we want the pin high. All right. Now, for the low part, let's see if I can do the low part. And so that would be, okay, we can just automatically see that if we've got 10 cycles and the high cycle is 6, then the low would need to be 4 cycles. 4 cycles low. And let me just check and do a little math real quick here. Is anybody still watching, or did everybody run off and watch silly cat videos, huh? Okay, I got 0.6 divided by. Okay, so yeah, that would be 4 cycles low and 6 cycles high. And that's going to add up to the 10 cycles, the 10 clock cycles. Now, if I have a 0, then what do I want? The high part over here on a 0, the high part is 0.35 microseconds divided by 0.125. And the high part of the 0 would be what? Let's put it in the calculator. And I get 0.35 divided by 0.125. And that says 2.8 cycles. And so what are we going to make that? We are going to make that 2.8 is going to be 3 cycles. And that's going to be 3 cycles high. And then what do we have as the other part? 0.8. And so I take 0.8 divided by 0.125, and that is going to be 6.4. But we need to go ahead and round it to 7, so we'll get the 10. And so that is going to be 7 cycles low. Okay, and you see this rounding is okay because we've got 1/10 of a microsecond. We've got 1/10 of a microsecond that we can be off by, and it will still work. So I need to, in the state machine, be able to create a 1. I do that by going high for 6 cycles, going low for 4 cycles. Now I need to make a 0. I need to be high for 3 cycles and low for 7 cycles. Okay, and this, I think I'm just going to look here. 6 and 4, that's right. And then 7 and 3, that's right. Okay, so that then all works out. Okay, now this is the thing that you would think is you would think, okay, let me just like go high and then everything will be okay. Or let me go low and then high. But if you're starting out low and then you give it the low part of the pulse period and then the high part, how can you tell that low from the idle? And so I tried several different ways. To generate this pulse. And like what I did was I came in and said, okay, let me do the low part and then do the high part. Okay, and you know what? That didn't work. So I said, okay, let me do the high part and then come in and do the low part. And that didn't work, even though I was generating this perfectly on the scope. The only way you can get this to work is you have to split the low state. So that means that you have to go low, high, low. Now this low and this low have to add up to the right low cycle, but that up pulse has to be somewhere in the middle of a low, a high, and a low. The high is all together, and you know how long that should be, but the low you've got to split into two different parts. And so this is kind of the way that I did it. So for a logic 1, what did I do? I came in low for one cycle. Okay, for a logic 1, I came in low for one cycle. That's one of a total of 4 that I need. I go up to a 1, and then I stay there 1, 2, 3, 4, 5, 6 for the 6 high. And then I come down, and how many lows do I still owe it? I owe it 3. And so then I go 1, 2, 3. And that creates a binary 1, or it creates a logic 1. Okay, now how do I do a 0? All right. Kind of very similar thing. So for the logic 0 here, I'm going to start with a low, all right, and then I'm going to go high. And then how many highs do I owe it? I owe it 3. So I'll go 1, 2, 3. And then I'm going to come low. And then how many lows do I owe it? I used 1. I owe a total of 7, so I owe 6. 1, 2, 3, 4, 5, 6. Okay, so this is the logic 0, and this is the logic 1. Okay, that is everything you need to know in order to control your NeoPixel arrays using the state machines. I've shown you how the data passes. I've shown you how to go from a Python array to go from that to a little groups of bits. And really what I need to show you, I guess the one other thing I need to say a little bit more about, maybe in case it wasn't completely clear. Okay, I need to send the data 24 bits at a time, because the 24 bits have all the information of what the first color is. The 24 bits have the complete packet of data for this one. So each pixel wants to have its own 24 bits. And so in the state machine from Python, I'm putting the data 24 bits at a time. And then the state machine reads it in 24 bits at a time, and then the state machine sends it to the pins 24 bits at a time. And so what you kind of do is you group your data into 24 bits. And remember, that was like that 0xFF is 8 bits, 8 bits, 8 bits, 24 bits. Okay, so you send the data out in 24 bits. Now, what I will tell you is if you don't do this exactly, counting the timing of every single line of code in your state machine, it's not going to work. This requires perfect timing for this to work. Okay, does that make sense? I hope it does. All right, now, if you're one of the people that really like a challenge, right? If you really like a challenge, then you can pause the video and you can go and see if you can make this thing work, okay? And, try it a little while. If you just can't do it, then don't feel bad. Come back and look at my solution. But I'm not going to pause the video and make a second lesson because I don't want to frustrate you guys. I don't want to frustrate you guys that this might be a little bit of a tedious, program to work. So you guys that are up for a challenge and are more adept at this type of programming, go ahead and pause it and see if you can do the homework. And otherwise, you can just kind of work along with me here. If you're tired, pause the video and watch it tomorrow, but I'm going to show you the solution. All right. Now, what are we going to do? In order to start, I am running out of space on my desktop. Okay. All right, so let's see. In order to start, we're just going to jump right in. We are going to need to import RP2. That's our state machine library. We're going to, from machine, import pin, and then import time, and then import NeoPixel. No, we're not going to use a library. We're going to write our own code. We're going to get down there at the bare silicon level and we're going to write our own code. We're not going to use a library. Okay, now we need to start. We need to kind of give notice that we're sending in machine code. So I'm going to do at rp2.asm underscore PIO. And now we're going to need to do a side set init. Okay. Now, a side set is where as I execute a line of code, exactly as I'm executing that line of code, I can set a different pin to a value. So I can say do this, do this, do this, like do this, do this, do this, but in parallel, do this as this pin is being set, do this as this pin is being set, do this as this pin is being set. So sort of with one clock cycle and one line of code, I'm doing two things and it synchronizes where they are happening at exactly the same point. And it's very hard to make this program work without using the side pins. So the side set init, I'm going to say that the rp2 dot, I need to make this bigger, right? Okay, like that. rp2 dot PIO and then underscore out, and PIO dot out and then underscore high. So I'm setting the side pin, that's going to be the pin 0. That's going to be the pin that we're sending the data on. I'm setting that high. Why? Initially it's high, and then what is our pulse train? Our pulse train is low, high, low. And therefore, it is going to see the low because I started high. And therefore it sees low, high, low. It absolutely sees the pulse train. Okay. Now, I hope this will work. Out shift dir is equal to rp2 dot shift rp2 dot shift underscore left. Okay, so you remember I've got like red, green, blue, which is FF0000, and then 0000, and then 0000 in hex. That is my, right, that is my color. Red on, green off, blue off. But now this one, the red is where over at the left. And if that's the first number, then I need to shift which direction? Left. Because if I shifted right, it wouldn't be getting 255 as the first number. It would be getting 0 as the first number. So since the 255 is the first number and it's on the left, we've got to move it that way. If that doesn't make sense, stop and pause and think about it a little bit. Okay, now what I'm going to do is I'm going to do an auto pull equal true, and I'll explain that in just a second. And then a pull thresh is equal to 24. Now you see, I can't afford to come in here and having Python do like a put to be putting data, right? I can't afford for Python to be putting. And so what this is going to do, and then pulling. What this is going to do is, how much does one pixel need? 24 bits. And so when the FIFO has 24 bits, the state machine will auto pull. So once FIFO has 24 bits, we'll get an auto pull, okay, an auto pull into the state machine. Now the state machine has got to be sitting there processing the data, but in parallel to that, I'll get 24 bits, it'll pull it, 24 bits, it'll pull it. Okay, so everything is centered around 24 bits because that is the color packet for one pixel: red, green, blue, 24 bits. All right, so now we have all of that, and then I think I can close that. That didn't like that. Oh, I already closed it. Okay, so that closes like that. All right, now we have to, now this is the bread and butter of the program. So I'm going to define my WS2812. That is the technical name of the NeoPixel. And so I'm going to put a wrap target like that. Okay, now we need to come over here and probably we need to be looking at, I'll show it to you here in just a second, but I think maybe this is the one that would be useful to look at. Okay, yeah. Is that the one that's useful to look at? No, I think it is. Man, I got kind of a mess here, don't I? Okay, this is what we want to look at here, this and this. So what do I want? You need to draw these things down. For a 1, I need to be down 1. Man, give me just a second here. I'm going to try to give you a view where you can look at that at the same time. This is doing some heavy duty. What is that? That is a camera. That is the wrong camera. You guys, please be patient with me. Okay, now I'm going to have this for you in just a second now, and I think you're going to be happy. Okay. I want you to be able to see this because this is tedious, and so I'm going to take a second. and get this. Believe me, this is more awkward for me than it is for you. Okay, there it is. All right, so you see what I'm trying to do? I'm trying to get you to see this because I've got to create that pulse train, right? So what do I want for a logic 1? I need to start, or a logic 0, either the logic 0 or the logic 1 is going to start with the 0. Okay, it's going to start with the 0. But what I got to think about is, where is my data? Okay, the data was put by Python. Okay, the data was auto-pulled. It was auto-pulled by the state machine up there. And where does it auto-pull to? It auto-pulls to the OSR. Okay, so then what I'm going to have to do is I'm going to have to, first of all, give myself a place to land. And so I'm going to say bit loop. That's not good. Bit loop, like that. Okay, so that's a place that I can loop back to. And let me just make sure about something that I said there. Okay, I just want to be very mindful about what I am saying here. Okay, yeah, so when you do the pull, it comes into the OSR. I was right, yes, everything's good. So where is my data going to be? My data is going to be in OSR. How many bits are in OSR? 24, because I sent 24 bits. You know, when we get down there, I'm going to send 24 bits in Python, and then when 24 bits get there, it's going to read it, and it's going to read it into OSR. But what is my problem? Now, 24 bits, I can't at this point handle 24 bits because I'm outputting to one pin. So I got to output those 24 bits 1 bit at a time. And the 1 bit that I have to output is got to be done in 10 clock cycles. And in the 10 clock cycles, I have to generate either this or this in the 10 clock cycles. So I have to do everything very, very carefully. So what is the first thing that I need? I need to shift out of the OSR, into X 1 bit. Okay, so I've got these 24 bits. I'm shifting which direction? Left. So the first bit that I'm going to get is the most significant bit of the red color. So if red is 1, 1, 1, 1, 1, 1, 1, 1, I'm going to shift that to the left, and I'm going to get that first one. I'm going to have 7 ones remaining, and then I'm going to have 16 zeros remaining. But I can't just burn that clock cycle. I've got to go ahead and set my side to 0. Why do I set my side pin to 0? Why do I set my side pin to 0? Because I'm going to be getting this or this. So you see, as I get that first bit out of OSR into X, whether it turns out to be a 1 or it turns out to be a 0, in either case, I need to start with that pin 0. It's 0. Okay? So it is set to 0. Now I'm going to jump. If not X. Okay, if there's nothing in X, I'm going to shift to do 0. Okay, do 0. So what does it mean if there's nothing in X? That means I don't have a 1. I did not pull in a 1. I pulled in a 0. And when I jump to 0, then I need to finish that pulse train as a 0. Okay, I need to finish that pulse train as a 0. And I need to mark this out. Okay, this is the 1, and this is the 0. All right, so in either case, I'm going to start with 0. And in either case, I have started as a 0 at the 0. Now, I want you to think right here. What do I want you to think right here? I want you to think that we've got the first clock cycle for either a 0 or a 1. If I end up here, I didn't jump, meaning I have a 1, okay? But I can't burn this clock cycle. I've got to tell this pen what to do at this clock cycle. So whether it is a 0 or a 1, what do I want? I want to come up. Okay, so whether I have a 0 or a 1, in both cases, I'm going to come up. Okay, so I've used how many clock cycles now? 2. And it's funny, for a 0 and a 1, they both want first clock cycle a 0, second clock cycle a 1. All right, but now if I end up here, that means I've got a 1. So then I need to no-op. I'm going to do nothing, okay? But I'm going to set the side to 1. I'm going to keep the side as 1. Now, for a logic 1, right, we're going to be looking at the logic 1 state here. I've done this. I've done this. And now, for a 1, I want to stay up for how many more clock cycles? 1, 2, 3, 4, 5, right? I've been up for 1. I want to be up for 6. So I need to stay up how many more? I want to stay up for 5 more. Now let me think about that. Yes. 1, 2, 3, 4, 5, 6. I want to stay up for 6. I have been up for 1. So how many more do I want to be up for? I want to be up for 5 more. It's going to say repeat this 5 times, like have this be there 5 times, but it was already there once. So it's 5 minus 1. So it's going to do the no-op side, and then it's going to do it 4 more times for a total of 5. Okay, but I write it this way so then I can count easier. This is up for 5, and then this is up for 1. So now I've been up for 6, right? I've been up for 6. Now, what do I need to do? I need to go down for 1, 2, 3. I need to go down for 1, 2, 3. So then I'm going to say no op dot side. And now, let's see. Let me think. The side, now this is going to be down for 3. Okay, this is going to be down for 3. This is going to be a 0. And it's going to be a 0 for how many? 3 minus 1. Like that. Okay. And now let's look over here and just make sure that we're thinking about this well. Okay, so now we've done that for 3. Okay, so we're down for 3. And now what are we ready to do? We are now ready to jump back and read the next bit if it was a 1. So now I'm going to say jump where to bit loop. Okay, and now what am I going to have? I'm going to have the dot side stay at 0. Right. So how many side zeros did I have? I had 3, and this one makes 4. That's 1 too many. So I'm going to back off this to 2, like that. Okay. I'm going to back off like that. Okay, so now I think I've created the 1 pulse. Now we need to create the 0 pulse. So we'll do a label, and then we'll do a do 0, like that. And now what do we want to do? Well, if we look over here on the 0, we've done this bit, we've done this bit, but now what do we need? We need 2 more 1s. So when I come down to the do 0, I can't add a side to that because that's not a real step. But what I do now is a no op and then do a side, and it needs to be at 1, and it needs to be at a 1 for how much longer? Well, 2 more, so 2 minus 1. Now, why am I doing 2 minus 1? Because the no op dot side is 1 cycle, and then I say do 2 more, so I say 2 minus 1. So 2 minus 1 is 1, plus the original one is 2. But it's just if I put 5, 2, 1, those are easier to count. So that needs to be a 1 for 2 more, and then I'm going to do a no op dot side. I'm going to put it at a 0. And now how many zeros do I need? So I've got this. Now I added those 2. Now how many do I have? 1, 2, 3, 4, 5, 6. So now I need to stay down for what? 6 minus 1, like that. 6 minus 1 is 5, plus the original one is 6. So now I've been down 6. Now I've created the 0. All right. And then all I do is wrap. Now, I think it would be better. I think a better way to do this would be, say, let's jump up to bit loop. And on that, let's do the side 1 for 6 minus 1. Okay. Instead of doing a no op, let's explicitly jump. So this is 1 plus 6 minus 1 would be 6. And that needed to be a 0. All right. Does that make sense? Does that make sense? I hope it does. Okay, so I am claiming that I've created a 1 and I've created a 0 there. Okay, now that is the really heavy lifting. Now we're going to go ahead and do the things we'll probably make a lot of mistakes on, but I'm going to create a state machine is equal to rp2.stateMachine, and it's going to be state machine 0. I'm going to use the WS2812 that I put up there. Our frequency was supposed to be what? Our frequency was 8 million, so that's 8, and then 6 zeros, 1, 2, 3, 4, 5, 6. And now we have to set that side set, right? And so my side set base is equal to pin 0, like that, right? And I don't think I need to initialize that. I think that's all I need to do. Now I need to turn the state machine on, so I'm going to say sm.active Make it a 1. Okay, I'm going to go ahead and just run this for typos. It's not going to do anything, but let's see. In line 5 already, in line 5. What out shift dir RP2 shift left. What is wrong with that? That looks pretty good to me. RP2 dot PIO dot shift left. So you see, it's good we're finding these little mistakes before we go. RP2 isn't defined in line 20. We imported RP2, state machine. What is that? Do you see, what did I do wrong? State machine is equal to RP2 dot state machine, and I imported RP2. What is going on there? It still is saying something about line 5. Out shift dir is equal to RP2 dot PIO dot shift left. Side set init equal RP2 dot PIO dot out high. Auto pull is true. Pull threshold is 24. And then that ends that. Oh, I know. Shouldn't be indented. Wow, that one scared me. Now let's see if we got it. Okay, now we've got no errors, so we can go in and we can kind of start trying to do our code now, right? Now, what we need to do is we need to create now the little routine that will write the pixel. So I'm just going to go ahead and I'm going to say, let's define write NeoPixel, and it's going to be sent data. Okay, and what data is it going to be sent? It's going to be sent that array of all the colors. It's going to be sent the whole array of all the colors. Let me see if I can show you that. It's going to be sent the whole, wow. It's going to be sent the whole my color array. Okay, it's going to be sent the whole my color array. And then I'm just going to leave this blank for now, and I'll come back and do it in a minute. But what are we going to need to know? We're going to need to know our num LEDs. How many LEDs do we have? Well, for us, it's 8. All right. Now, what else are we going to need? We're going to need to create a data array. So I'm going to put some really neat colors in. So I'm going to say that I've got my color, and I'm going to create a blank array. So I'm going to create an array of zeros times num LED. So I'm starting to try to build my array now. All right. Now, my color is going to be equal to, and I'm going to open the array. I'm going to open the array and now open the color, and I'm going to have a color 64, 154, 277. All right. And then my next color is going to be, that's pixel 1. Now pixel 2 is going to be 128, 0, 128. And now comma. And now the third pixel is going to be 50, 150, 50. You can make your array whatever you want it to be, but now I am to pixel 4, and that's going to be 255, 30, 30. Okay, and now I'm going to have 0, 0, 128, 255. Yeah, we would never know if we didn't enter these colors right, because no matter what we do, we're going to get good colors. And so now it's going to be 99, and then 199 and 0. Okay, and then I'm going to get 128, 128, and 128. That's going to be kind of like almost a white. If I say it one way and type it a different way, do what I say, not what I type, okay? Now that's not happy for some reason. Okay, we'll keep going. And then the final one is going to be 255, 100, 0. And then we'll close the color, and then we'll close that. Okay, so that looks all happy. So now I have a pretty color array in there. Now I'm going to say my right NeoPixel. And what do I send it? My color. Right. So you see, that is the way we normally think. Now this has to break it down and has to create the bit stream that we're going to send, but it's really pretty easy. This part is pretty easy. So what we need to do is we have 8 colors. We have colors. We have 8 colors. So what we're going to do is we're going to step through those colors. So for color in data, you know what I'm going to do? I'm going to call this, I'm going to catch the data as colors. Okay, so for color in colors, what am I going to do? Well, now I'm going to call the 24 bits that I'm going to send. I'm going to call that, is it, yeah, it's 24 bits. I'm going to call that GRB. And that's going to be equal to what? Well, remember, color of 0. Color of 0 is red, and that's on the left, right? But what do we want to do? We want to shift it to the left by 16. And then remember, we are going to OR that. That is the shift key above the enter. We're going to OR that with color of 1. And we're going to shift that 8 bits to the left. And then that's the red, that's the green. And we're going to OR that with the blue, which is going to be color of 2. Okay. And then we don't actually, I don't even know. I don't think I need that. I don't think that is good to have there. Color 0 to the left 16, color 1, and then ORed with color 2. I think that is how we can do it. I'm not sure if I don't know if I need parentheses around that or not, but we will find out. Now, what do I have? I have 24 bits, right? I have 24 bits that is the color of the first pixel. The red value, the green value, and the blue value. All right. But now, I did it that way so you would understand RGB. And what did I send? RGB. But here, I did it that way just so you would understand it. But now the NeoPixel doesn't want R followed by G followed by B. What it wants is, it wants you to send the green first, and then the red, and then the blue. So this first number should not be red. It should be green. And the second number should be red, which would be 0. And then the third number would be blue, which would be, it wants the blue, which would be 0. Okay, so red, green, blue. So green, is that right? I think that's right. No, that is not right. It wants what first? It wants green first, which is 1. Then it wants red, which is 0. And then it wants blue, which is 2. All right, now the moment of truth. The moment of truth. I want to sm.put grb, and I want to put it 8 bits at a time, because then that way with 8 bits at a time, it will send green, it will send red, and it will send blue. Now I'll pull another 24 bits, and then with that new 24 bits, this will be for NeoPixel number 2. It will send green, it will send red, it will send blue. Okay, like that. How many mistakes did I make? This could be a long debugging session, but let's switch over here and let's see what happens. Okay, it doesn't like line 32. Okay. Oh, that was what my problem is. It's not an IP address. It is commas. All right, let's try that again. Boom! Look at that. Look at that. And I just wish you could see how beautiful those colors are. I wish you could see how beautiful those colors were. Oh my goodness, those are beautiful colors. You can't capture on here very well. So let's do some numbers that we would know. Let's just see if it does what we really think. Let's send red 255, and then so the first NeoPixel is going to be red. So that would be 0, and that would be 0. Okay, so that's red. The next one, let's make green, so that would be 0. So you see, I put them in the right order, red, green, blue, and then up here, I mix them up the way that the NeoPixel wants them. So 0, 0, 255. Red, 0, 255, 0. That would be green. And then 0, 0, 255 would be blue. So let's run that. So this time, what do I expect? I expect red, green, blue in the first, second, third thing. And this will really kind of debug it. Okay, boom, look at that. Bright red, bright green, bright blue. All right, now I'm going to see if I could see it better. What if we turn these down and maybe the camera could pick them up better? So I'll turn it down like this, see if there's any improvement in the way that you can see it by turning the brightness down. So let's try that. I think that works a little better. Now, red, green, blue. Now let's do cyan, which is blue and green. So this would be 0, red, and then green, and then blue. So that's cyan. Now magenta would be red and blue. And then this would be 0. And then cyan, magenta, and then yellow would be red. And then this would be green. And blue would be 0. So we've got that. And then, then this would be white. And then, so let's just look at that and see what happens. Okay, boom, look at this. Red, green, blue, cyan, magenta, yellow. Let's make the next one, orange. And orange would be kind of like yellow with more red. So let's say 200, 128. No, I'm sorry. This one we're going to make no. That was yellow. Now this we're going to try to make orange by 200, 100, and 0, like that. Okay, so cyan, magenta, yellow, or red, green, blue, cyan, magenta, yellow, and then indeed we did get a lot more of an orange there. Okay, and let's just do something interesting. Let's make the last one full white, 255, 255, 255. Okay, yeah, we got a bright white out there. Okay, guys, this was a tedious lesson. You guys need to give me feedback, because if this is just too much for you, if this is just too hard, and if it's too tedious and you're bored and you want to go back to just, doing simple things with libraries already, let me know, because this was a pretty hard lesson to put together. I'll tell you, the really hard thing for me was the fact that if I just gave it an up and a down, it didn't work. If I gave it a down and an up, it didn't work. The only way it would work would be if you split. If you split your timing, if you split the 0 and you had a low, a high, a low, and you kept the combination of the lows the right length and the high the right length, it worked. But I tried everything, like, why doesn't it work if I start low and go high? Why doesn't it work if I go high and go low? And I could find absolutely no documentation on it. But when I found some of the libraries that people use, they were splitting the 0 too. So it's a mystery. No one seems to know, or no one's saying why you got to split the 0. But if you don't split the 0, then it doesn't seem to work. And so I thought this was pretty good. Okay, you guys, for homework, let me see if I can find a good homework for you. I know some of you guys maybe did this as a homework, but those of you that just kind of followed along with me, now what you can come in and do is you can create like a really neat pattern using the state machine that we just created. Now, creating the pattern, right, when you create the pattern, you're not monkeying with the state machine, because you can't touch the state machine, because that you can't touch the state machine. Where am I here? You can't touch the state machine because the state machine timing is perfect. But what you are doing is, let me come over here. What you're doing is you're creating this my color array, and in Python you manipulate the my color array to make something beautiful happen, like this. And we call this the running rainbow, because each pixel is running through the rainbow of colors, and then the rainbow is shifting across. So you make something beautiful on your NeoPixel, and let's see who can come up with the most pleasing and soothing and beautiful sequences of color on the NeoPixel using our newly developed state machine code for controlling the NeoPixel. Okay, guys, I hope you are having as much fun taking this class as I am making it. It is at this time that I always give a shout out to you guys who are standing with me on Patreon. When I make these in-depth teaching lessons, I don't get hundreds of thousands or millions of views. I get a few thousand, because most people just want to copy and paste the code and just get the schematic and then do something cool. So there's a lot fewer people that want these in-depth lessons. And so the only way I can do this is through my Patreon supporters. Thank you guys for standing with me. You can also help me by giving this video a thumbs up and leaving a comment down below. If you haven't already subscribed to the channel, when you do, make sure that you ring that bell, and most importantly, share this video with other people, because the world needs more people doing engineering and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.